Well, Jerry, I don't have any kind of bio or anything usually on these open forums, so we'll if you want to kind of lead off with what Woodrow was looking for, and then we can
Okay.
kind of just roll into maybe the next set of questions after that somebody might have. But
All right. Can I get control so I can throw up my PowerPoint
sorry,
here?
you're good now.
Okay. So let me. Okay. Is it showing up on the screen?
Not yet.
Okay. Let me try this again. I got so many screens open here right now that it's. All right. Well, while I'm getting this figured out, because it's been a while since I've done this, question came up about just some general COGO information. Doing some COGO intersection type of things. What the heck? Why is it not coming up?
Yeah, the question was a review of common COGO routines in
Right.
boundary surveying. So.
And let's see, why is it not showing up? Share screen. Well, Jiminy Christmas. Let me close some of my other ones here. But anyway, while I was figuring this out, let me just a little bit of background with respect to COGO. Coordinate geometry is based on triangle solutions. There's a couple different approaches that one can take to coordinate geometry problems. And probably the easiest one, or the easiest one to do manually without software, is to do it based on triangle solutions. And when you do triangle solutions, you have to remember that when you're solving triangles, there are basically 6 parts to a triangle, 3 angles and 3 distances. And you need to have 3 pieces of a triangle to solve the other parts of the triangle. At least one of those pieces has to be a side. You can't solve the triangle geometry or fix a triangle if you just have angles in a triangle. If you think about an equilateral triangle, there's all sorts of sizes that can have and not be fixed physically. But as soon as you fix a side of a triangle, then it fixes the other geometry of a triangle. Do we have anything up there yet?
Oh, something.
There
we go.
There we go. All
You're
right.
good now.
I'm going to go all the way back to the very beginning.
You're good now.
Okay. Like there's a lot to COGO besides just this intersection. There's a lot of background type of stuff, trigonometric relationships and all that kind of stuff. But this, we're just going to look at the intersections and using basic triangle geometry to solve a position of a point. Now, when we're solving a point position, and we're going to restrict it to 2-dimensional at this point, although 3-dimensional is basically the same thing. We're just adding an additional position and an additional measurement. If we think of it as there's 2 unknowns at a point, there's a north coordinate that's unknown and there's an east coordinate as an unknown. So in order to establish those 2 unknowns, you have to have 2 things, 2 measurements that connect it to another position that's known north and east. And probably the simplest way is the forward calculation, when you've got a direction and a distance from a known point, then you use the latitude and departure to get the coordinates of point C from point A. Okay. Or you could do the same thing from point B if you have the coordinates of point B in the length and the direction from B to C. Now, you don't have to have the same 2 measurements from one point. You can have 2 measurements from 2 different points. So in essence, I can have a distance from A and a direction from B. That's my 2 knowns to solve the 2 unknowns that are up here in any combination of those. So that's basically what COGO is. It's using 2 other points and connecting those through 2 measurements to a 3rd point to establish the position of that 3rd point. And basically what we're creating is a triangle. Once we have the coordinates of these 2 points here, A and B, that becomes our baseline. And we can inverse calculate between those 2 and determine the length of that baseline as well as its direction. Well, if we compute the length of that baseline, that gives us the side of a triangle that we need. We always need to have at least one side of a triangle when we're solving a COGO intersection. So the other two measurements are going to be either the distances from the baseline points, or angles down here to get our other two parts of the triangle that we need. So any two measurements that help us establish the coordinates of that point up here from off of our baseline. Now, there's basically three fundamental intersection types. Now, when you go into software, whether you use Civil 3D or Traverse PC or any other software, you go into the intersection routines, and there's like a million different intersection options that you can pick from. But they're all fundamentally some variation of these three, because you're solving basically a triangle. It's a distance intersection, distance direction, or an angle distance, and a direction. So in each of those cases, we're going to look through the logic for the solution of this point position off this baseline for these three different methods. And we're just going to kind of look conceptually, how would we go through that to solve that manually? Now, in a distance intersection, basically we start with point A and B. That's our known baseline, and we shoot a distance from those two endpoints to that point that's unknown. So we have our knowns here, and then we have these two sides that we get. So the way we start solving this is we start putting together our triangle. Now, ultimately, the way we want to get the coordinates of that unknown point is with a forward calculation from one end of the baseline or the other. And that is to come up with a direction and a distance from either A or B to get point C. So we solve enough of the triangle to do that. Now, in the case of a distance intersection, there's two possible solutions, because we have a mirrored triangle solution here. We can have either the red triangle or we can have the blue triangle. Now, we make a decision based on what makes sense in the context of the problem that we're working with. Is the point, say, northwest of our baseline, or is it southeast of our baseline? Software doesn't know that. It can't figure that out logically. So generally, when we're doing this type of intersection in software, we have to either give it an additional piece of information, or the software will generate for us two solutions, and it says, pick one. Okay, and then we have to make the decision as to which one we're going to select and solve for. But these are mirror solutions. These are mirror triangles. They're the same angles at the points A and point B and at point C, and all the distances are the same. So we got to make a decision. So I'm going to pick point C1. And I want to solve for that guy right there. So now I need a direction from B to C or from A to C in order to get the coordinates of C here, doing a forward calculation from one end to the other. So in order to do that, I'll inverse first along the baseline. So I'll establish the length and the direction of this line here. Then I want to compute, say, this angle up in here. And then once I have this direction and this angle, I can get a distance in the direction from point B to point C to get that. Well, how do I get an angle up in here? If I've got three sides to a triangle, how do I start solving the angles for that? Anybody have an idea? Can I use law of sines? It's America. I can do anything I want, right? No, you can't use law of sines, because you have to have at least one angle in order to use law of sines to solve for the other angles and that type of thing. Whenever you have three sides, you have to use law of cosines to solve. So law of cosines, you have to use that to solve for this angle up at B here. So I'm going to use law of cosines to solve for angle up at B. And once I do that, then I'll have this angle. I've got this direction. I can add, in this case here, I can add that angle to this direction to get the direction of this line. Now I can do a forward calculation using latitudes and departures to get from B to C. My math check would be to compute the angle down here. Now, when we're dealing with coordinate geometry, we generally start with just enough information to be able to solve the problem. Okay, so for instance, if I go back to my original premise here, these distances, if I transpose 2 digits on my number that I had for the distance here, as long as it resulted in an intersection here yet, I would still wind up with coordinates of this guy, but they would be wrong. And I wouldn't know it because I have just enough information to solve this situation. That's one of the reasons we normally don't rely on 2 measurements. For those of you that remember doing survey ties for points, you never use just 2 ties to tie a point to monuments on it. How many ties did you use as a minimum? Anybody do ties? Anybody do any guys? You always did 3 ties. Why'd you do 3 ties? To resolve this problem right here, right? As soon as you tied to a 3rd point, one of these would go away, okay? Because it could only be one of those 2 solutions. So whenever we're dealing with COGO in this context here, we're shooting these distances off this way, we have just enough information to solve for that point. So when we solve our triangle pieces here, and we come up with coordinates of this guy here, and then we say, well, we're going to solve for this guy down here and do a forward calculation from point A here. We'll get the same exact coordinates that we will get from point B, but they'll be wrong because everything's based on a wrong measurement up in there. So we have to be really, really careful in that respect. Now, the other thing with COGO, once we start solving triangle pieces, you saw that when we started with 3 distances here, the way we had to start solving was using law of cosines. There was no other way to start solving that problem. You had to start with law of cosines. Once we got one of these pieces solved, once we solve this, if I want to solve this angle down here for my math check, now I can use law of sines because I have an angle. I can use either law of sines to compute that angle, or I could use law of cosines. The more pieces I have, the more ways there are to compute the remaining pieces. So that's my distance intersection. A math check would be, again, to compute from the other end. A distance direction intersection, or a distance angle intersection, we've got off of one point, one end of the baseline, a distance, and from the other end, we have, say, a direction. So where these intersect, they give us this intersection point right here. Now, we got to be careful with a distance direction intersection because there are actually 2 different intersection points that occur. We can intersect this distance along this line of sight here or along here. Okay. So we actually wind up with 2 different triangles in here. And actually, this is when we talk about law of sines and using the law of sines to solve angles and stuff like that, our calculators will always give us an angle for the law of sines when we're solving it at angle less than 90 degrees. So our calculator is always going to give us this angle down in here, where sometimes we need this angle up in here. So we've got to make a decision again, which point are we solving for? So make that decision, which one we're going to solve for. Let's say that we're going to start solving by doing our inverse calculation here for our baseline again to establish distance and direction. So now we've got a length of our side, one side, length of another side, and we have an angle in here now because we have a direction and we have a direction. So we have 2 sides and an angle. So we have the a side-side angle triangle solution. Now, when we use the law of sines to compute the angle here, because we have a side, and then we have an angle and an angle here. So if we want to use this is to, the sine of this is to this, as this angle, sine of this angle is to this, when we compute this with our calculator, it's going to give us an angle less than 90 degrees. So we got to look at it and say, if we compute that angle and it comes out as 60 degrees out of our calculator, it's either going to be 60 degrees or it's going to be 120 degrees. It's 60 or 180 minus 60 or 120. So we have to make a decision as to which one of these 2 we're solving for, because it's going to have an effect on the positions of those points on that point right there. So let's say we decide that it's this one right here. It's greater than 90 degrees. So we're going to take whatever our angle comes out of our calculator and subtract it from 180 to get the angle in here. Now we've got enough information that we can start solving the other angle using the angle condition for a triangle, 180 degrees. And we can do compute this side here from the law of sines, and then we could do a forward calculation from point B. So it's always which parts of the triangle do we have to start with? Which ones do we need to be able to allow us to compute a direction and a distance from one end of that baseline and then do a forward calculation? So when you think about it, there's three distinct steps involved in COGO. One is an inverse calculation to establish the baseline on one side of the triangle. The other is using law of sines, law of cosines, and the angle condition to compute enough other pieces of the triangle to allow us to do the third calculation, which is a forward calculation from one end of the baseline to the other. So we're kind of bouncing back and forth between different operations using trigonometric relationships in there. Now, when we do a direction-direction intersection, a direction-direction intersection only gives us a single intersection. So there is no ambiguity in a point position. We start with a direction at one end and we start with a direction at another end to establish this coordinates here. Now in this case here, we don't have any distances involved in our measurements, only directions or angles off the baseline. So in this case here, we again start with an inverse calculation, establish that side of the baseline. And once we have the lengths, and we want to convert these directions into angles down here. So now because we have a direction of this line and a direction of this line, we can compute the direction, the angle here. Same thing up in here. We take the inverse or the back direction of this line and the direction here and compute that angle right there. So now we have a side, angle, angle, and we want to start solving for this side and this side here. So now how do we solve for this side or this side? Any guesstimates? What's the first thing we need to do? Can we use law of sines? This would be to the sine of this as this is to the sine of this. Can we solve it doing it that way? No, because we don't know this and we don't know this. Can we do it using law of cosines? Well, law of cosines relates three sides at an angle. Well, we only have one side and two angles, so we can't do it law of cosines, okay? So what do we have to figure out first? This angle up in here. How do we get that angle in there? This plus this have to equal what?
180.
180 degrees. So once you have this angle, once you've got that angle, now you can use law of sines with this side and this angle, and then you can compute either this side to this angle or this side to this angle. And then once you've got the sides, then you've got enough information to do a forward calculation to get the coordinates of point C from there. Now notice that this one only has one intersection point, but in this one here, there are no distances that are measured. There are only directions or angles measured. It's only when there's a distance involved that you have multiple solutions. Let me back up here. See, there's a distance involved, so you have multiple solutions. If we go back to a distance-distance intersection, you have a distance-distance intersection, you got multiple solutions. So it's only when there's at least one distance involved that we got two possible solutions for the intersection point. And again, 3 dimensions, it goes just, you know, an additional measurement and an additional dimension, but basically it's the same concept, same type of mathematical concepts. All right, so now I said that there was a bunch of other intersection types, but they're all fundamentally drawn off of this. If you do a lot of road design or dealing with subdivisions where you've got curves and you're intersecting boundary lines with curves or road-to-road intersections and that type of thing, you'll have arc-arc or circle-circle intersection types of problems. And those are basically just distance-distance intersection because your center points of your radius points of your arcs are your baseline points. And then your radii are your distances. So just like we've got a distance, had 2 solutions for a distance-distance intersection, we have 2 solutions for an arc-arc intersection, 2 radii. Same thing with a direction arc intersection. When we're intersecting, say, a property boundary to a cul-de-sac, say, it'll intersect at 2 different points because you've got the center of the cul-de-sac, the radius of the cul-de-sac, and then the lot line coming through there at a direction that can intersect at two possible locations. All that is radius point and radius, which is basically a distance direction intersection. So most other types of intersections are a variation of those three fundamental intersection types. Now, there are other ways to solve intersections. Using trigonometry or using triangles is probably the simplest way to do it manually. You can do it using arcs, going back to this type of stuff, using circle equations and arc equations and that type of thing. It's just that those aren't as fundamentally easy to remember as law of sines and law of cosines to do intersection solutions, even though they're probably easier to program in that context. Let's look at an example with some numbers in it. And I will have this available for posting. I've got a couple of examples and I won't go through all of them, but kind of talk our way with respect to working with some numbers and establishing coordinates. So in here, we want to figure out what are the coordinates of point G off this baseline from T to S. And in this case here, instead of having a direction, we've got a variation of a direction distance intersection. We've got an angle distance intersection. We're at point S, we've got an angle measured from T to point G, and then from T to G, we've got a distance. So it's a variation of the angle of the direction distance intersection. So, but the solution logic is basically the same. We've got two sides of a triangle that are represented in the measurements. Our third side comes from the coordinates that we have for the baseline here. We can inverse between these and then we get our third side. So we'll have a side, and an angle for our triangle. What we want to do then is we either want to establish a direction of this line to do a forward calculation from these coordinates, or do a forward calculation from here, which means we need a direction of this line and a length of that line. So in this case here, if I remember correctly, we do it off of point T. So we'll just do a calculation off of there. So we'll inverse from T to S. And a good rule to use whenever using differences in surveying is it's always the to coordinate minus the from coordinate will always give you the correct sign, correct mathematical sign on stuff. So if I'm going from T to S, it's always going to be the coordinates of S minus the coordinates of T. That will always give you the correct signs on things. So if I do my inverse calculation, and these are the equations I use for that, my differences in north and east, my length, and then my alpha is using the tangent function, is the angle off the meridian, either clockwise or counterclockwise to the line. If it's clockwise, it's the northeast or the southwest quadrant. If it's counterclockwise, it's in the northwest or the southeast quadrant. And that tells you how to add it to 180 or to 360 to come up with the azimuth of that line. Again, that's some of the background information with inversing. But from that, we can establish the length and the direction of the line from T to S. Now, we want to get to the direction of this line right here. So if we back up here a second, we've got a distance, and we've got an angle. To get to this direction here, we need this angle up in here. To get that angle there, we can use the law of sines. This is to the sine of this, but we don't have this angle or this side here to get this angle in here. What we do have is this side right here, and we can compute this angle using law of sines. So if we go to law of sines here, this is to the sine of this, as this is to the sine of this, we can compute the angle right there. Now, that angle is going to come out using law of sines as 75 degrees, 24 minutes, 23 seconds when you hit the inverse sign on your calculator. So first thing we do is we look at point G at that angle up there and say, is that less than 90 or is it greater than 90? Because it's less than 90, we use the 75 degrees as it is. We don't have to subtract it from 180, because otherwise it'll also be point G could intersect over in here and be that angle greater than 90 degrees and still meet that sine condition. So I always want to double check that, because that's that duality because of that distance involved here. So in this case, we'll accept that angle, which means that this angle down here, using the angle condition, 180 minus this plus this gives us this. Now we have an angle and we have a direction. We can compute the direction of this line, and we have the distance from here. We can now do the forward calculation from there to there to get the coordinates of point G. And if we want, we can do the math check from point S. Okay. Simply by computing this side right here and then using the forward calculation there. Okay. All right, one more here, and then we'll toss it open to see if there's any questions or comments or any other information that's necessary. This one here, we've got a distance intersection off of 2 points here. So with a distance intersection, we don't have any angles involved. So we know right off the bat that because we have 3 sides to a triangle, we have to start solving a triangle using the law of cosines, because law of cosines relates one angle to 3 sides. So in this case here, we want to either do a forward calculation off here or off of here. So we need the direction of this line or the direction of this line here. So if we first do an inverse, now I'm going to go from point 30 here. So I established the length and the direction of this line here. So I got my 3 sides. To compute this side here, I'll use my law of cosines. Now, law of cosines is not ambiguous like the law of sines is. Whenever you take the inverse cosine of something, it'll always give you the correct number from 0 to 180 degrees on a calculator. It's not ambiguous like the law of sines can be. So in this case here, we have that angle there. And because we have this direction here, we can compute the direction of this guy. And once we have that direction, then we can do a forward calculation from here to here. So it's pretty straightforward. When you follow the logic, I'm not gonna go through this third one, but basically what you're doing is you're always starting with an inverse, then you're solving pieces of the triangle using law of sines, law of cosines, and the angle condition to get enough information so that you can do a forward calculation from one end of the baseline or the other, okay? Now, unique solutions. If I go back to the distance intersection, I have to back all the way up here. The distance intersection, okay. The 2 distances have to add up to a distance longer than the baseline length. Otherwise, they don't intersect. So we have to have at least these 2 distances greater than a baseline, or you'll get a non-solution type of thing. When we have distance direction intersection, the only way that you'll wind up with a unique solution with only a single intersection solution, what condition has to be met at point C for there to be a unique solution, only 1 point for the solution here?
I'll be a shill. AC cannot be bigger than AD.
Right, but for right now, I've got 2 possible solutions for C, right? C1 and C2. Under what condition will there only be 1 solution for point C?
Okay, where the circle is tangent.
Right, there you go. Because in this case, C1 is greater than 90 degrees. In this case, C2 is less than 90 degrees. When C is equal to exactly 90 degrees, then you've got a tangent intersection, and there's only 1 possible solution. In essence, you have a right triangle that you're solving for, okay? And then for this one here, for direction intersection, what condition do we not want to have? We don't want those 2 lines to be what? We don't want this line and this line to be what? In order for them to intersect, they can't be parallel, right? If they're parallel, they'll never intersect, okay? So even if they're slightly off parallel, at some point they'll intersect. They want to have a big, long isosceles triangle or whatever, but you don't want these 2 to be parallel in order for them to not intersect. And software, when you give it combinations of information like that, hopefully it's written well enough such that it won't blow up on you, but it'll come back and it'll say insufficient information or intersection not possible. But if there is multiple solutions, whenever there's a distance involved, you're going to wind up with 2 potential solutions. That's why you have to give the software additional information, or the software will give you two solutions, and it's up to you to make a decision as to which solution is it that we want to use. Okay, that's COGO, quick and dirty. There's a lot more to it than this. There's a lot more tools and stuff associated with COGO with this. We start introducing curves, tangent, non-tangent curves, and that type of thing. But for the basic intersections type of stuff, the question that was about basic intersections, hopefully this addressed most of that stuff. There's a lot of information on my website with respect to coordinate geometry, COGO. I'm going to do a shameless advertisement here for my website, if I can pull it up.
I'll grab it, Jerry. I'll put it in there.
Okay. And I have a lot of example problems, and I also show how to do the COGO calculations using arc geometry as opposed to just triangles and stuff. And there's a couple of spreadsheets up there also that you can try out different types of things to see different intersections and that. So are there any questions? Let me escape. Let me quit this and turn off the...
Jerry, while you're waiting for questions, I have a comment.
Yeah.
I found when I teach intersections that it's not a bad idea to include using that thinking to also solve for perpendicular offsets.
Yeah. As a matter of fact, in my class lectures, I always threw in, when I talk about variations on intersections, I always threw in the thing about right angle offsets, and the fact that they're kind of a special type of calculation, because you're turning to the right or to the left 90 degrees and then doing forward calculations from there. So yeah, that's just another variation on the thing. And also, I just talked about here generically about solving stuff, but if you think about it in terms of where does a piece of equipment sit when you're actually making these measurements, because your baseline points don't necessarily have to be intervisible. And a distance intersection is a good example of something like that. You could be sitting with a total station at point C and then shoot to points A and B. And A and B don't have to be intervisible. You just need to be able to have their coordinates so you can calculate stuff. So another way to think about it is, where can I put my equipment to make these measurements? And as long as I'm out there, what additional measurement can I throw in as a math check? You know, because not only can I do that distance shot from point C, but I can also measure that angle at C. And I've got a third piece of that, another piece of that triangle for a math check. So yeah, it keeps on going.
That's awesome.
Hey Trent, can I
Yeah,
share my screen really quick?
absolutely. I think
If I de-shared you,
Jerry will stop
Okay.
sharing, then you'll be
okay,
able to
there we go. You should
go.
have it back now. You got it?
And then we can always, if you will share that PowerPoint, I'll get it in the Dropbox link for
Yep.
everything. So that'll be great.
Can y'all see my screen yet or no?
Yep.
Yeah,
We have your
yeah.
triangle solutions up. That's good stuff.
Yeah, this page kind of summarizes the 6 potential options of COGO working. So yeah, these 6 options here, and I explain what kind of situation it is. I have a diagram there, and then below each one of these, I have the order to solve that problem. Like Jerry was saying, angle, it's impossible to solve. There's nothing you can do about that situation. You're going to have to get a length of at least one side, just like Jerry stated. But all these others, that's the process that you would have to do. So one of the examples you just showed was an angle side, or was it? I forget. But look at number 2, angle side. The first thing you would do is you have 2 angles, so you can automatically calculate your third angle in this situation by the summation of angles of a triangle. It always has to equal 1/8. So if you have 2 angles, the first thing you're going to do is generate that third angle, and then you can use law of sine or cosines accordingly. In this situation, you'd use law of sines. So these are the options that you'll be presented, and these are those distance, distance, and direction that Jerry was just talking about. They're all wrapped up in here. And you know, you guys were talking about law of sines, law of cosines. I have the formula for each one of these here. So yeah, I just wanted to show that if y'all want to do like a screenshot of this right here.
Yeah.
To keep for.
The only thing I want to caution on again is whatever you wind up using the law of sines to do your first step for your solution, is to always, when you get that angle coming out in the law of sines, immediately look at the triangle and see if the angle that you're solving for is less than 90 or greater than 90. Because your calculator will always give you the angle that's less than 90. Even if you've got the canned routines on your calculator, like a lot of them do, where you just put in the pieces of triangle, it'll always give you that one back. But you got to look at and see if my angle is greater than 90 degrees, then I have to take that angle that the calculator gives me and subtract it from 180. So that's the thing you got to be careful with the law of sines all the time.
Yep. And then, also, Jerry, like you were saying, the first step for any of this is going to figure out that baseline that you called it. You know, so if you have this point and this point, and you have northings and eastings for each one of those points, the first thing you're going to have to do is calculate the distance and the bearing, or the distance and direction.
Right.
And like Jerry said, the way you do that is through your departures and your latitudes. So you're going to be creating a right triangle. Okay. You're going to have the departure is going to be your east-west direction. That's departure. And then your north-south direction is going to be your northing. And that's going to be your latitude. So from those two, you know, if this is, I can work one really quick. I can make it up. Let's say it's 0, 0. So this is at the origin. And then let's make this one 100, 100. Okay. So by doing that, I know that my, and Jerry had the equations for this, the change in northing. So your delta of northing is going to give you your latitude. What is change in northing? It's the distance from here to here.
Sure. Oh, okay. You got it. Yeah, it's the
Yep.
For those he's doing it on his phone, which he's got an overhead view. If you
Dane,
if you double click on his
your phone, that would be good.
Yeah, if you double click on his video on the right hand side, which is his top view, you'll be able to full screen it, and then you
Sorry
can
about
follow
that.
along. That's okay.
Yeah. All right. So you got your origin 0, 0, and you got this point 100, 100, and we're just going to figure out the bearing and distance right here. Okay. This line is the hypotenuse of this right triangle, right? And you're going to have your latitudes and your departures, east, west, north, south differences. So my change in northing is going to give me my latitude. And that's going to be from the change from 0 to 100. So my change in northing is going to be 100. And similarly, my change in easting is going to be 100. So my delta in easting is my departure. That'll be 100. So I know I have 100 feet here and I have 100 feet here. My latitude is 100 feet. My departure is 100 feet. Now, solving for right triangles, you can use Pythagorean theorem, or you can use, if you know an angle, you can use sine, cosine, or tangent. This situation, we don't have an angle yet. So I'm going to have to use the Pythagorean theorem. A squared plus B squared equals C squared. Okay. So it'll be 100 squared plus 100 squared equals X. This is my X squared. Okay. So it'd be 10,000 plus 10,000 equals x squared. 20,000 equals x squared. Square root of x squared, square root of 20,000. And let's see. Yeah, good. 141.421 equals x. So I know this distance is 141.421 feet. Okay. Now, now that I have three sides, now I can generate an angle here if I wanted. And that would be done by, let's just pick one, sine, okay? So sine of this angle is going to be opposite over hypotenuse. Sine equals opposite over hypotenuse. Okay, so sine of x, let's make this x. So sine of x equals opposite 100 divided by hypotenuse. Let me do that real quick. 100 divided by sine of x equals 0.707. Inverse sine of that, I'm going to get my value of x, which will be my angle. And the angle is 45. X equals 45. I should have known that because this is a, these two sides are even, so it has to be 45. But yeah, that's the idea. This working right here is going to be the very first step to anything that you do with COGO. You're going to have to establish a bearing and a distance on one of your lines. There's no way around it. And the way you do that is you just break it up into right triangles. I mean, 95% of all surveying math is right triangles.
Right.
And if it's not that 5% that isn't, you probably have to use a right triangle to get started anyway, you know? So knowing how to do this should be like the back of your hand. This should just be very much as a second nature. So
Good stuff. That's awesome. Does anybody have specific questions on this particular topic at the moment before we move to something else? I know there's a couple of you studying. I think Kyle, you got any specific questions that you might want to ask? No, Kyle, he stepped away.
Oh.
I know he's not shy, so that's not the issue.
yeah.
I saw in your, I was thumbing through your book real quick because I know what you have on the screen is part of your manual. So starts on page 54 of your fundamentals exam book. So those of you that are looking for that, I did throw that in the chat as well. So there's a whole section. Go ahead, Joe.
Throw in a couple of comments here.
Absolutely.
With respect to all these calculations and stuff, and the calculators that are allowed to be used on the exam, be real careful which calculators you can bring into the exam. One of the things that I've discovered with my students when I've taught for the last number of years is there's confusion on how to do basic trigonometric functions and manipulations on your calculator when you're dealing with degrees, minutes, and seconds, and decimal degrees, and conversions, and back and forth. And I noticed that on the exam, the Texas Instruments TI-30 family of calculators can be used. Which is a real simple calculator, but within the TI-30 family of calculators, the way they work with degrees, decimal degrees, and degrees, minutes, seconds conversions is not consistent. So be real careful that you understand on your calculator how to do conversions, how to do trigonometric functions, and do like inverse. Like when you do an inverse sine, using a lot of sines to solve for an angle and stuff like that, when that angle comes out, is it coming out in degrees, minutes, and seconds, or in decimal degrees? Because it's going to have an effect when you use it for subsequent calculations later on. And I can almost guarantee you from having writing licensing exams and stuff in the past myself years ago, if you use decimal degrees as degrees, minutes, and seconds that come up with a wrong answer, that wrong answer is going to be in a multiple choice list.
Yep.
Because that's a demonstration of whether you understand how to do your calculator. So
Absolutely.
keep that in mind. And also the other thing that students underutilize on your calculators a lot are parentheses to group operations on chain calculations and memories in your calculator for storing intermediate results to minimize rounding errors and that type of thing. So it's a matter of knowing your calculator and being fundamentally comfortable with doing chain calculations with your calculator. That's kind of fallen by the wayside a little bit lately because everybody's dealing with computers and stuff now to do most of the calculations and that type of thing. And we're starting to lose the art a little bit of understanding the numbers that we're dealing with when we're doing manual calculations and stuff like that. So be real familiar with your calculators and how to effectively use them for memories and sorting operations and that type of thing.
Yeah, I want to add to that. I strongly suggest the calculator that you study with is the calculator you bring into the exam. I don't know why you wouldn't do it that way, but
Exactly.
I mean, if you're using it to study, it needs to be the calculator that you take to the test. And you should know where the buttons are just by feel. Kind of like your Trimble tablet out when you're surveying in the field and you're hitting buttons before it can even computate what you're trying to do. That's how you should be treating your calculator. And I also recommend the simplest kind of calculator you can get. If you're going in there and you're relying on formulas or all these programs in your calculator and stuff, that's fine. But you should also know how to do it the longhand way as well. I'm not saying don't program your calculator. I'm just saying it's probably a good idea to know the math behind it, And I'm telling you right now, the math behind survey is not that difficult. We're talking law of sines, law of cosines, and how to break down a right triangle. If you can do those and like a proportion, knowing how to do like single proportioning. So, yeah, I just wanted to add the calculator that you study with should be the calculator you take in. This is the one I've passed every test with. It's the simplest TI 36 you can get, and it's solar powered. That way I never have to worry about getting batteries. I just made the assumption that I'm sure the examination room is going to have a light in it somewhere. So that's all I need.
Yeah, great information. It's awesome. There's a couple of good ones in the chat too. Jason says you should know your calculator like tying your shoes with your eyes closed.
Yeah,
exactly.
Yep.
Good point. Jen says study the owner's manual for your calculator too. Not all the buttons are obvious.
Yep.
And the HP35S is a beast to find the little multi-key function definition. So
yeah,
good information.
If y'all can still see my screen, the degrees, minutes, seconds to decimal degrees conversion, the manual process is in my book as well. Y'all can do a screenshot of this if you need, but all this can be done in your calculator with the punch of one button. So like Jerry said, don't underutilize your calculator. Don't spend the 1.66 minutes you have to answer a question. Don't spend it converting decimal degrees to degrees, minutes, seconds, because that should take you literally 1 second, So Yeah, just keep that in mind.
Nice. There's a couple of people jumping off, but anybody going back? Anybody have some specific questions they want to ask or want to talk about? Want to hear about?
Can you hear me now?
There, yeah, you were there, and then there you go, Kyle. Go for it.
There we go. Yeah, I was just going to mention also on that TI 36 thing, when you're taking the test, they actually have that up in like the top left part of the screen. You can bring up a TI 36 itself. So if you bring your HB 35, but you want to do some of that simple math, you always have that up there. Just wanted to kind of
good.
point that out.
On the computer screen?
Yeah, I heard they
Yeah.
have
Okay.
a digital calculator. I didn't know it was this one.
Nice. Okay. Good information. Thanks, Kyle. Cool. Anything you wanted to cover, Dane, for tonight?
Let me see. We could do intersection of lines real quick.
Okay.
So this is kind of like another step to COGO. It's still COGO, but I haven't done this in a while. I might be kind of rusty. If no one else has anything to do, I can talk about this. But so let's say you knew, let me see. Let's say you have the only information you're given are the northings and eastings of two lines. And what do I mean by that? So if you look at my diagram here, you can see where you have two lines. And line one, my northing and easting of my first point is 1, 5. My northing easting of this point is 15, 10. Then I have northing easting of this line is, let me see, 4, 11. Yeah, 4, 11. And 10, 5. Let me make sure that's right. So X and Y, X, and then X. All right, I think that's right. So these are essentially my northings, eastings, but they're presented to us in X and Y, okay? So don't forget, northing and easting is really Y, X, right? So all these flipped would be my northing, easting. So northing easting for this would be 11, 4, right? So how do you solve to figure out how these points intersect right here? What's the coordinate of this intersection point? I go through all the steps on how to do that, okay? And it involves these 4 steps right here. First, you have to figure out the slope of each of the lines. Then you have to figure out the y-intercept. Then you have to plug that information in to figure out the x value and the y value of the corresponding line. And I'll go through it really quick. So slope. Everyone remember what slope is. It's the change in y divided by the change in x. It's also known as rise over run. So think about a staircase, okay? Rise is how far the step goes up. Run is how far the step is extended into the other stair, okay? So rise, run, rise, run, rise, run, rise, run. This line right here will have a slope based on those rises and those runs, okay? So the change in y, which is the change in elevation or northing, divided by the change in how far that staircase is, okay? that'll give us the slope. And it simply is delta y divided by delta x. So if I go back over here, I can figure out the slope for each one of these lines, okay? It's just gonna be, let's take this line. It'll be the change in rise over the change in run, change in y over change in x. So for this line, if I go from 1, 5, y and x to, I'm sorry, xy, to this xy, it'll just be 1. Oh yeah, that's another part here. You always have to keep everything consistent, okay? You can't choose this y. Let me do it out here. So change in y, so it'd be 5 minus 10 divided by 1 minus 15, okay? I kept these correlated with the point. What I mean by that is I didn't flip it around. I didn't say 5 minus 10 divided by 15 minus 1. Okay. If I choose point 1 to be the first number in my y, I better be choosing 0.1 to be the first number in my x. Okay. You got to keep it consistent. You could do it the other way. I could have chose this is going to equal 10 minus 5 divided by 15 minus 1. These two will equal the same thing, okay? All right, so I figure out my slope for this. 5 minus 10 would be -5 divided by -14. So it'll be 5 divided by 14. I get 35.35. Okay. 357. All right, so that'll be my slope for this line. And slope is designated with an M. Okay. Then I'll do the same thing for this guy. I come up, if I do the math for this, I come up, I get a slope of -1. So it's slope of -1, slope of positive 0.357. That's step 1. Step 2, find y-intercept. What is y-intercept? Okay. Y-intercept is known as B, and it is the value of y when x equals 0. So let's take this line again. What is this line? Okay, and I got my Cartesian graph here. 0, 0's there. So this is my y-axis, okay? What is y going to equal if I were to extend this line and intersect the y-axis? That right there, that point right there is going to be my y-intercept. All it's saying is, where does your line cross the y-axis? That's y-intercept, okay? And the way you figure that out is, let me see, that's going to be a y-intercept formula. Y-intercept formula is B equals y minus mx, okay? Now notice, it requires a y value, an x value, and a slope. Well, we already figured out the slope. That's why it was step 1. So let's figure out the y-intercept for this line right here. Y-intercept for that line is going to be B, and it's going to equal, I'm sorry, and the definition of y-intercept is where x equals 0, okay? So I know x right here is going to have to be 0, because wherever it intersects the y-intercept, the y-axis, x will equal 0, right? That's why it's on the y-intercept, the y-axis. So in this formula, I know my m and I know my x. That's going to have to be 0. Let me see. Make sure I'm doing this right. Okay, so I have B. Oh yeah, you just pick any point you want. Okay. And we only know 2 for this line. So I have my Y value and my X value. So B will equal Y, which is 5, minus, I'm using the slope of this line, which is 0.357, times my X value, which was 1. Let me see. Yep. So if I do the math on this, B, my y-intercept is going to equal 4.643. Okay. So when X is 0, Y will be 4.643. That's my y-intercept. Okay. So I would do that for both of these lines. I could do that for this one. B equals Y minus MX. I'm going to pick this point here. B equals Y is 11 minus my slope was -1 and my X was 4. If I do the math for this, y-intercept on this line will be 15. Okay. So this line, if I were to extend it up, it would intersect the y-axis at 15. And down here, it's going to be 4.643. All right, so that's step 1, slope. Step 2, find y-intercepts. Step 3, determine the value of intersection. So I'm going to be determining the X value of this point right here by setting each line's slope-intercept form equal to one another. So what do I mean by that? So line 1, the y-intercept form is going to be my intercept, my let me see. No, I'm sorry, my slope intercept form is going to be my y-intercept form when I solve for M. Okay. No, when I solve for Y, sorry. So I would have to bring Y over, bring B over, and I'm going to get my slope intercept form. The slope intercept form is Y equals MX plus B. That's slope intercept. And y-intercept is B equals Y minus MX. Okay. Again, it's just algebra to switch between the two. So the third step in this situation to figure out the value of that point is going to be to set line 1's slope intercept equal to line 2's slope intercept. So Y equals MX plus B is going to equal MX plus B for line 2. Now I'm gonna have to pick a point. Let me see. Yeah. So the slope for line 1 we found to be 0.357. So 0.357. X is what we're solving for, plus y-intercept of line 1 we figured out to be 4.643 is going to equal, so that's line 1. Now line 2 is going to be my slope, -1, X plus the y-intercept for line 1 we figured out to be 15. So now I have this equation, and I'm going to be solving for X in this equation. So the way I would do that is bring 15 over here, divide each side by 0.357. If I do all that algebra, I get 7.632 equals X. Okay. So by setting the two slope intercept forms equation equal to one another for each line, solving for X, I'm going to get the X value of 7.632. And that tells me the coordinate for this value right here. So I don't know y yet, but I know that x equals 7.632. Now I got to solve for y. I have my x, I need my y. So the way you do that is you just pick your y, your slope intercept form again. Y equals mx plus b. And I plug in my x value. Okay. I found x, so now I can plug that value into my x here. So y equals 7.632. Okay. Now what m and b do I use? I can choose whatever I want because the coordinate for this intersection, I can find it by using this line or this line. So let's use this line. Let's use the line with the slope of 3.357 and the intercept of 4.643. Okay. So these are the two values that I'll need to plug in to this equation. And I could do it with this line too. I could use -1 and 15 if I want. Either way, I'm going to get the same answer. So, -5, I'm sorry, 0.357, y-intercept of 4.643. Yeah, let's do the math because in my example, I use the other line. So let's use this. Let's do the math on this one. 0.357 times 7.632 plus 4.643 equals 7.367. That's going to be my y value. Okay. And I did, in my example here on the screen, I used the other line, and I got the same answer. Okay. So again, you can use either line. In step 4, you can use either one. Doesn't matter. The value is going to be the same. Again, because you're figuring out the only point those two lines have in common. So now I know my y value is 7.367. 7.367. So the value of where that line and that line crosses is right here. And the value is 7.632 is my x. My y is 7.362. This one, x was 7.632. This one, 7.367. Okay. So that's how you figure out the intersection of lines. Okay. And you may or may not have to do this on the exam, but knowing how to do this does set you up for a pretty good understanding of slope and y-intercept and the Cartesian graph, knowing northings and eastings, aka x's and y's or y's and x's. So knowing this kind of it's a real good summary for a lot of good mathematical concepts. Okay. So I'd recommend knowing how to do this, whether or not it's required for the exam. It's gonna get you familiar with grading and slopes and all kinds of other concepts. Okay.
It's good stuff, Dane. And then for those that do have Dane's book, it starts the example that he just did is basically page 91 through, you got, I think it's 91 through 93 in your book. So yeah, can kind of follow along or go back and kind of redo the sample with him and watch this video again, since there's a lot of moving parts to that one.
Yeah, no, there is. And that's exactly why I want to bring with understanding COGO. I always bring this one up because it's like the it's kind of like the Holy Grail, you know?
Sure.
You have to
Okay.
understand a lot of other components to be able to do this. And it's not difficult. You just got to follow these 4 steps. And it's very important to, when you're finding out those slopes, to keep your points organized. If you're pulling your deltas for this point first, then pull them first for the X as Y, the X as well as Y. Okay. And I explain that in the book too. Just keep them all lined up. And it doesn't matter which way you do it. You can start with this point and subtract this point, or this point and subtract that point. Doesn't matter. Just keep everything lined up.
Does most of everyone on here know about Dane's book and or have a copy of it? It's a good book. It's $40. I put the link in the website for those that want to purchase it. And
Thank you.
Dane can get it out.
Yeah.
But yeah, it's really good stuff. So kind of what we go through on a lot of these open sessions or these study group sessions, a lot of it either comes from Jerry's website or it'll come from Dane's book. So definitely both of those are good informations.
Yeah. Yeah. Thank you too, Jerry. Next week, I've been almost every week I've been focusing on mathematics, survey computation stuff, but we should spend 1 week going through a lot of legal concepts, easements, deeds, descriptions, rules of construction, stuff like that.
Yeah, absolutely.
That
Dr. Paver, I just found your email. So he wants to do one on weighted bearings, which will be a good one. And I'll send you an email back on that, Dr. Paver, but maybe the August 2nd is the next open session. So if you're available that night.
Yeah, I was going to say, if you, sometime when you have time, I just sent it as an example of things that I can do.
Yeah, no, it'd be fantastic. Anything to help for sure. And then definitely get the information out on your website as well. So he's got Dr. Paver's got the one called GeoLearn, which I also put the link in the website, the chat as well.
Oh,
so.
yeah. Yeah.
Yep. So everybody, lots of really good resources here. Jason, I saw you were looking for just kind of gathering all your stuff. So there's a couple other, Indiana is doing a study group session. Kyle is still on here, but he's sounds like he's roaming around, but Kyle is doing one for in Oklahoma as well, for Oklahoma's young surveyors. They're getting together. So and I believe even Texas has kind of started a session as well. So there's lots of these, kind of like what we're doing tonight, happening via Zoom, all kind of across the country in different states. So
You've started a trend, Kent.
right.
Trent.
Yeah.
Trent, do you know if there's any study groups in the Northeast? I do a lot of work with surveyors in New York.
I don't believe so. Jen is up in that area. She's a college student at UMaine. I don't know if Jen, have you really seen much going on in that area? If you're able to unmute. Oh, there you go. Cool.
I don't see a whole lot of anything going on. We're sort of disconnected because I'm an online student, so I'm not really, I'm sort of just me.
Right. Okay.
And Melcy does their regular workshops, but there's not like a study group. And we have a young surveyors group, but we haven't really sort of done anything organized together.
Okay.
Jen, is that young surveyors group you're referring to for Maine?
There's no, for Massachusetts.
Okay.
Yep. Sorry, I'm in Massachusetts, and but I'm in UMaine online program.
Yeah.
Right.
I'll also kind of chime in on a shameless plug here.
No, go for it, Kyle.
OSU OKC also offers a purely online summer course for FS review specifically.
Oh, wow.
I mean, I took it and then passed it a week later, so I don't know if I have too much, but like too many. I haven't talked to too many other people who have taken it, but I would definitely recommend, not only study groups. Yeah, we've got one with Indiana and Texas and Oklahoma, and then we're looking at branching out in those aspects in other states. I've actually talked with the U of Maine, their doctor surveying up there a little bit about starting one up there as well. Mainly just getting the word out right now is what we're trying to work on. And if Jen or anybody else wants to join up, we're actually having our last session with Indiana Young Surveyors, I believe, next Sunday. But it's always good to get on just to ask questions, whatever we can do to help.
And then I do have all of those. The Indiana stuff is all recorded, and I'm working on going to get those on the Mentoring Mondays website. So all of that Indiana study group stuff is recorded. I'll get them loaded here, hopefully in the next couple of weeks. But I was looking to see. You said it was Oklahoma State, Kyle.
Yeah,
Okay.
OSU, Oklahoma State University, and then at Oklahoma City, they have a survey technologies course. It's a 2-year degree, but as part of that, they offer an FS specific review. It's a summer course. I
Okay.
believe it's like $300 or $400 for an 8-week course, but I mean, it goes over all of the above.
Awesome. Yeah, I see the Oklahoma State website. I was just looking to see if I can find something on that particular class, but yeah. So there you go, Dr. Byron. There's lots of stuff going on for sure. But I know the UMaine student body is really good. I mean, there's a couple of hundred students at UMaine, so I'm sure there could be something super beneficial for the Northeast area for sure.
So I
Yeah,
should say that we also have like a whole course that's exam prep.
Okay.
So, which they waive if you pass the exam before you take the class, but
Okay.
you know, for what we need to study, there's a whole course for that.
Cool. That's awesome. Good.
I actually went to the University of Maine in Orono for my surveying courses. That's where I got my first license, was up in Maine, and it's an unbelievable school. It really is. Well, it was back when I did it. They had Knut Hermanson and Ray Hintz. I mean, those guys are as top notch as you can get.
We do have Knut coming up in September.
Oh, I can't. I'll definitely be there for that one.
He's doing adverse possession. He's going to be September and October. He's going to do another one on prescriptions. So.
Oh wow! Yep.
So it's good. Good stuff.
Yeah.
Okay.
There are a couple other good survey schools out there represented tonight.
Yep. Right.
Is Dr. Paiva still with Missouri?
Yep.
I'm with a couple of institutions here.
Yeah.
Missouri University of Science and Technology, but they just have a single course for their civil engineers. But we have a program for people wanting to get licensed in Missouri. Missouri has kind of a strange set of education requirements for licensure. You don't have to have a degree, but you need to have 12 semester hours in surveying, 3 of which need to be in legal aspects. So we offer those at State Tech, and I don't teach them all anymore, but I pre-recorded lectures to make it easier for the instructors, so they still use my lectures for surveying 1 and 2. And then actually, so the main guys or the people in the Northeast know I used Don Wilson's land records book for the land records course, which is mostly documentation, descriptions, research, that kind of thing. And then I do legal aspects, which pretty much there's Wilson again. It's now Browns, Wogelard, and Wilson, as most of you know. And then those of you who know Dick Elgin, who's been on Mentoring Mondays, he does a state-specific section as well.
Got it. I was just trying to find, I know Dr. Elgin has the Land Surveyors Review course coming up as well in about a month or so. I was see if I could find the link for that.
I'm actually teaching part of that.
Yep.
I think it's 16th, 17th, 18th.
Okay. Yep. I was trying to find
and you can slice and dice. So on the 16th, we mostly cover a lot of the stuff we've talked about today. We start with basic algebra and geometry and kind of race through trigonometry and get to the applications. A lot of that is intersections and basic COGO. I tell people, if you can't hand calculate this situation, you set up with your total station on a point, you backside another point, you want to set a new point, and you're doing the whole thing by hand, and all you have are the coordinates of your occupying station, the coordinates of the station you want to set, and the coordinates of the point you're backsighting. If you can't do that, you're probably not ready to take the exam when it comes to the COGO side of things.
Yeah, very good. Very good points. My shameless plug, right? I went to the Land Surveyors review course August of 2004. And I loved it. It helped me pass. I know that back then. So I'll find some information on that, and I'll share that part out as well.
Yeah, I can send you the flyer if you want.
Okay, perfect. Yeah, and I'll put it in the follow-up email. So
in fact, the third day of that course is all the legal aspects of the Missouri minimum standards, all the statute law, because for those of you who don't know, in Missouri, the state-specific exam covers stuff from the USPLS that's totally different from any other state in the union except for Arkansas. Like we have double corners in every township, for example.
Mhm.
And so that day's presentation will actually be available virtually. Anybody who wants to log in will be able to access it. And actually us, GeoLearn, will be providing the resources to make it a hybrid event instead of just an in-person event.
okay, great. That's
So
awesome.
I'll send you the flyer.
Okay, cool. Yep, I'll get it all set up. Okay, well, just to be respectful of everybody's time, and we're at 5:30, so I appreciate everybody. Jane and Jane. I blended both of your names.
Yeah.
Jerry and Dane. I definitely appreciate it, and then looking forward to. Thanks for the input, Dr. Paiva, and we can look at having you do that presentation in August too. Just kind of give these boys a break as well.
Thanks, Jerry and Dane. Have a good evening.
Exactly. Awesome,
Yeah,
guys.
everybody. Thank y'all.
Awesome.
If anyone
you,
has any
guys.
questions, just reach out to me.
Yep, same here.
Yep.
Yep.
I'll throw both of your guys' emails in there. So in the
Okay.
follow-up email.
Thank you.
Awesome.
Trent, always thank you.
Thank you guys.